All right, so next up we're solving this equation right here, x squared y double prime minus 3xy prime plus 3y equal to 2x to the fourth e to the x. And what I'm going to do is first I'm going to kind of explain how we think about this problem and set the stage for the work that we'll do on it, because it's the type of problem that you learn how to solve in a different section, but it uses tools from this section. And I think that sometimes when you learn those tools separately, it's hard to remember how they belong back together in the end. So if I'm explaining stuff that you already know, just kind of like sit back and accept it. But if you kind of struggle with figuring out when to apply the different tools we learn, this would be a good time to kind of like stop and think through that process. So first of all, x squared y double prime minus 3xy prime plus 3y equal to 0 is a Cauchy-Euler problem. And we learned how to solve that, or we're currently learning how to solve that in this section. But x squared y double prime minus 3xy prime plus 3y equal to 2x to the fourth e to the x is a variation of parameters problem. So it's non-homogeneous. So it's either variation of parameters or undetermined coefficients. But since you have things that depend on x in front of your derivatives and y, that means that you have to use variation of parameters. And we already learned how to do that. But we need y1, y2 from like step 1 to solve y sub p in step 2. Our general approach to solve non-homogeneous equations what we always have to do is solve the homogeneous. That means whatever you saw in the differential equation equal to 0 part first. For what we called our fundamental solutions. y1, oh no, sorry about that. y1, y2, so on and so forth. Then we can actually use the methods that we learned in the last couple sections. To find y sub p, that one particular solution. And then superposition, an idea we talked about in the first section of like exam 2, tells us the y would be c1, y1 plus c2, y2. However many of those solutions you find right there, plus your y sub p. And because the previous sections were about doing that non-homogeneous part, I just feel like you haven't seen a lot of examples where you weren't given y1, y2 to start and then moved forward in the problem from there, where you've actually had to sit down, find y1, y2, then remember to do the non-homogeneous part, and then put it all back together. That's why I'm trying to be really deliberate about explaining that way of thinking for this type of problem. So now that we've kind of made that map of how we approach this type of problem in general, what that means for us is first we need to solve the homogeneous problem of 1 minus 3, 3. So x squared y double prime minus 3xy prime plus 3y equal to 0. So all I've done is I've taken our differential equation and ignored the non-homogeneous part. We set it equal to 0. That's the first thing we always do when we see this type of problem. And then once we've done that, we kind of think about all the different ways that we know to solve second order problems. And we see that because there's this x squared y double prime, this xy prime, and then nothing on y, this is a Cauchy-Euler equation. So we solve it using y equal to x to the m. So that means if y is x to the m, y prime is m times x to the m minus 1, and y double prime is m times m minus 1, x to the m minus 2. And then we just plug that into our differential equation. We have 0 should be x squared y double prime minus 3xy prime plus 3y equal to, oops, I put the 0 on the other side because that's easier. If we should have that, but we just said that, sorry, the weather is extreme. We just said that y double prime is m times m minus 1, x to the m minus 2. We said the y prime is m x to the m minus 1. Said that y is x to the m. When we remember that x squared times x to the m minus 2 is x to the m, and x times x to the m minus 1 is x to the m, what that gives us is m times m minus 1 x to the m minus 3m x to the m plus 3x to the m. And we can factor out that common x to the m to give us m times m minus 1 minus 3m plus 3 times x to the m. So all that is stuff that we've been doing in this section. I've been explaining less of the algebra and arithmetic as we go on, so hopefully none of that went too fast. Maybe pause and make sure you're with me up to this point. But our auxiliary equation to solve for m is going to be m times m minus 1 minus 3m plus 3 is equal to 0. So that gives me m squared minus m minus 3m plus 3, or m squared minus 4m plus 3 is equal to 0. And that's just going to be m minus 3 times m minus 1 equal to 0. Because minus 3 times minus 1 gives you positive 3, but minus 3m minus m gives you minus 4m back. So the roots are going to be m equals 3 and m equals 1. That's going to give us solutions. y1 equals x cubed and y2 equals x to the 1, so just x. And so normally, if we were just solving that equation like we were in the rest of this section, we would kind of say y equals c1 x cubed plus c2 x, and we would draw a box around it, and we would say we finished this problem. But this is just one part of a longer problem. So now that we have those two solutions, we're going to go back to the non-homogeneous part and then finish out the problem. So I'll do that in the next video so that this one doesn't run over. Just click on through whenever you're ready for that.